Welcome back to the deep dive. We pull apart your source material and distill the insights that matter most. Today, we're wrestling with a cognitive profile that presents a truly compelling paradox, a rare, profound ability for structural understanding. This ability to visualize complex concepts in three, four, or maybe even more dimensions coexisting right alongside, well, documented inefficiencies in basic sequential operations like linear arithmetic or rapidly retrieving a known word.
It really is the definition of cognitive unevenness, isn't it? And for us, the challenge is moving past just the descriptive labels and getting to the mechanistic how. This isn't just a fascinating anecdote, about a highly intelligent person who struggles with certain tasks. Our mission today is really to unpack the precise, highly structured architecture that supports this powerful multidimensional thought, specifically known as three-dimensional visual thinking, or 3DVT.
Okay, let's unpack this then. We've got deep research detailing the profile of Denis Verhage, whose cognitive structure is really the foundation of our dive today. We're going to look at how a cognitive strength, which is often used as a compensation strategy, actually mirrors some of the most powerful concepts in modern mathematics and, maybe surprisingly, in advanced computer science too.
Right. The core takeaway we want you to leave with is a clear understanding of 3DVT, how this structured, multidimensional thought functions as a precise, highly reliable tool for solving genuinely complex cognitive problems. We'll move through, let's say, three stages. First, the geometry of this thinking, linking 3D-VD to the rigorous mathematics of tessellation.
Okay.
Second, the neurocognitive engine that maintains this structure, which we're calling tabular coherence maintenance.
Right.
And finally, how this very specific human architecture has, in a way, become the engineering blueprint for modern large language models and artificial intelligence.
It sounds like a study in cognitive resilience meeting technological emulation. So let's start with the foundation, geometry, because our sources define this nonlinear thinking using, well, one of the most rigorous tools in advanced mathematics. When we talk about three-dimensional visual thinking, 3DVT, I think a lot of people immediately think of maybe spatial reasoning tests or just being good at rotating shapes in your head. But the sources define this ability in far more sophisticated terms, specifically linking it to the mathematical concept of tessellations. Could you maybe walk us through the actual rigor behind that term?
Certainly. So, to start with the mathematical foundation, a tessellation is defined as the covering of surfaces or spaces with geometric shapes. Crucially, without any overlaps or any gaps. It's like the perfect tiling of a space.
Like tiles on a floor, perfectly fitted.
Exactly. Now, as the sources point out, most people probably know this through the aesthetic beauty of, say, M.C. Escher's art, where you see these incredible interlocking patterns of birds or lizards.
Very visual.
But the sources are really insistent here. This is not merely an aesthetic pattern.
Okay, so the sources, and they're referencing specific articles on hard science, they really emphasize the functional utility of this geometric arrangement. It's not just pretty.
Precisely. The aesthetic component is secondary to the functional rigor. Tessellations are powerful, precise mathematical tools. They are, in fact, the analytical foundation for addressing highly complex problems in disciplines like geometry, complex analysis, and even theoretical physics. The necessity of having that precise, gapeless fit is what allows mathematicians to model extremely complicated phenomena where continuity and structural integrity are just paramount.
Can you give us maybe a concrete example of that application? Why is a tessellation a better tool in those fields compared to, say, just a linear equation?
That's a great question. A linear equation describes a path, right? A to B. But a tessellation describes a field. Think about studying material science or fluid dynamics. You can't really solve for the behavior of a complex liquid flow or the structure of a crystalline material using simple A to B steps. You need to model the behavior of the entire space simultaneously, ensuring that every point, every single data element, is correctly related to its neighbors without any informational voids or contradictions. A tessellation provides that necessary structural formalism, that guarantee of comprehensive integrity for the model.
Right, that structural integrity. That sounds like exactly what the 3DVT mind is striving for. The sources define Denis Verhage's 3DVT as a form of advanced cognitive tessellation or even symbolic tiling. That suggests the mind is applying that same rigorous mathematical mandate to symbolic content like language, relationships, concepts, not just geometric shapes.
That's the monumental leap, isn't it? 3DVT involves creating these multidimensional structured arrangements where abstract symbols and geometric elements fit together seamlessly, perfectly in mental space, forming these cognitive tilings. This is the brain's own high-fidelity mechanism for achieving deep structural understanding. It doesn't process information sequentially. It builds an entire interlocking architectural model of meaning.
And the most important quality here, you mentioned it before, is this absolute need for geometric coherence. No gaps.
Absolutely. Just like a physical tiling has to be continuous and gapeless, in the 3D-VT process, concepts, symbols, relationships, they must all be arranged in a continuous, gapeless pattern. Imagine trying to understand a complex philosophical argument or maybe a massive geopolitical issue. A typical mind might use a flowchart, maybe a list.
Yeah, linear steps.
The 3D-VT mind, instead, is mapping all variables, historical data, economic models, ethical implications, whatever, onto a single, coherent cognitive geometry, where every piece connects logically, structurally to every other piece. That tiling prevents conceptual voids, or, just as importantly, logical inconsistencies.
This complexity is where the three-dimensional part of the name starts to feel a bit, well, maybe inadequate, because the sources suggest this thinking actually matches the concept of tessellations extending into 3D and even beyond, into what are called hyperbolic spaces. What does visualizing in hyperbolic space even mean for abstract thought?
It's a really powerful metaphor, I think, for capturing immense complexity without limits.
Yeah.
Classical 2D tessellations are flat, and standard Euclidean 3D space tiling is still fairly intuitive, like stacking blocks.
Right.
But hyperbolic geometry is non-Euclidean. It's geometry on a curved surface that expands incredibly rapidly. The classic example is like a saddle shape. Cognitively, it reflects the multidimensional, nonlinear, and potentially recursive nature of truly deep abstract thought.
So it's not just stacking ideas like Lego bricks, it's the ability to visualize relationships between concepts that maybe increase exponentially in connection.
Precisely. Hyperbolic space technically allows for an infinite amount of tiling within a finite area. So in the context of 3D VT, it reflects the mind's capacity to recursively connect and integrate an almost unlimited number of variables and subconcepts, all within a coherent structure. It's why this kind of thinking aligns so well with complex analysis and function theory fields, where the relationships between variables are inherently nonlinear and demand massive integration.
And the sources mention structural and aesthetic unity.
Yes, the resultant tiling has to feel right. It's crucial. The framework must possess both structural rigor, the mathematical precision, and a kind of self-contained aesthetic balance. This ensures the cognitive model is not only logical but also intrinsically satisfying, stable in its holistic structure.
It really sounds like the mind is deploying the same level of architectural precision you'd need for, I don't know, high-level engineering, but applying it to abstract knowledge instead of physical structures.
That is a perfect summary, actually. We are talking about a mind that inherently organizes information according to the foundational mathematical laws that govern complex systems, ensuring the knowledge isn't just acquired, but structurally engineered for maximum reliability and potentially predictive power. This rigor is achieved because the individual is almost driven to map complexity geometrically.
Okay, so we've established the structural result, this geometrically perfect, multidimensional cognitive tiling. Amazing stuff. The question now, though, is how do you actually maintain a structure that complex? What's the operational framework that keeps all those hyperbolic connections stable? That brings us to what the sources call tabular coherence maintenance.
Right, tabular coherence maintenance, or TCM. This is the process we identified that frames this kind of sophisticated human cognition as a structured, multidimensional form of active reasoning. It's essentially the engine dedicated to managing that perfect cognitive tiling we just described. And the very first point we have to emphasize is its complete departure from standard linear thought.
Which most of us rely on, right? A causes B, B causes C. We build these logical chains.
Correct. Linear thinking is sequential, it's often time-based, and it tends toward reductionism, breaking things down. Tabular reasoning, in stark contrast, operates across multidimensional relational fields. It's a structure inherently built for cross-domain synthesis. The sources conceptualize this structure as a kind of conceptual matrix, an immense mental table.
Okay, let's try and flesh out that spreadsheet of meaning analogy a bit more. If you're listening, try to visualize this really complex, dynamic table in your head.
Okay, imagine a massive living data table. The rows might encode specific situational contexts, maybe particular lived experiences, or historical data points. The columns then might encode abstract principles, laws of physics, ethical frameworks, mathematical rules, personal values, whatever fits.
And the cells, where they intersect.
Exactly. The individual cells where the rows and columns intersect are the points of synthesized meaning. But the key is the entire matrix, this massive table, embodies the individual's geometry of meaning. And it's not static. It's constantly being checked, updated, verified.
That sounds less like storage and more like a system designed for constant comparison and validation.
Absolutely. The process requirements for maintaining coherence are simultaneous and incredibly demanding. You need cross-domain synthesis, constant symmetry checking, and anomaly detection. So if you introduce a new concept, say a novel piece of scientific data, the brain-running TCM doesn't just, put it in a separate folder.
Yeah.
It instantly checks that new data point against all intersecting rows, contexts, and columns, principles, to see if it causes a logical gap, like missing information or an overlap, which could be a contradiction or maybe just a redundancy.
It's like an internal verification system designed to constantly resist logical flaws or inconsistencies. Wow, the cognitive cost of maintaining a field this complex must be enormous.
It is, which really confirms that this isn't the standard mode of thought for most people. It's a specialized high-resource strategy. And to handle that massive, simultaneous, non-linear integration, you need highly specialized and distributed brain networks. This is where we start looking at the neural correlates that seem to support this cognitive strength.
And the sources immediately point to the rostrolateral prefrontal cortex, the RLPFC network, as being crucial here. What exactly is its job in maintaining this massive conceptual matrix?
The RLPFC is essentially the ultimate manager and synthesizer. It's widely identified as the headquarters for executive synthesis, that's the region responsible for handling high-level planning, and the management of multiple abstract ideas simultaneously. So in the context of TCM, the RPFC is what allows the system to manage the, frankly, dizzying complexity of the tabular mapping. It's constantly overseeing those symmetry checks and the anomaly detection across all the different domains.
So, if the brain were like a big organization, the RLPFC is the chief architect, maybe, ensuring the structural integrity of the entire building, overseeing the whole global workspace integration.
Precisely. That's a great analogy. Without the RLPFC operating at peak efficiency, that intricate geometry, that tiling, would immediately collapse into just disconnected data points. It's the engine that prevents information from becoming isolated islands of fact. It ensures that when you retrieve a piece of information, you're retrieving it fully within the context of its entire relational matrix.
But that abstract design still needs maybe a foreman to handle the spatial mechanics, right? The
Right.
parietal cortex is mentioned as the partner in this structure.
Yes, the parietal cortex is the critical node for spatial and relational processing. If the RLPFC is the chief architect defining the abstract rules and relationships, you could say the parietal cortex is the foreman, making sure the physical or spatial arrangement holds together. It's necessary for arranging, manipulating, and comparing those multidimensional data points across the cognitive table, quite literally anchoring the geometric tiling structure in mental space. It gives the abstract knowledge a kind of spatial reality, which is absolutely essential for 3D VT.
Ah, okay. That helps explain the three-dimensional nature more clearly. The parietal cortex is giving this abstract knowledge a spatial dimension, so the RLPFC can manipulate it efficiently.
It essentially creates the mental canvas for the symbolic tiling to happen on. And we can't forget the temporal limbic network either. This network isn't just about cold logic. It also links these complex cognitive constructs with effective significance.
Meaning that the abstract knowledge isn't just cold and clinical data, it actually has emotional resonance or personal meaning attached to it.
Yes, exactly. The temporal limbic network assigns symbolic salience and emotional relevance. It ensures that the knowledge constructs are linked to their meaning and relevance within the individual's broader worldview, their experiences. This is really key to long-term memory integration and also self-correction. If a structure feels right or coherent, that effective response reinforces the validity of the tiling, helping to integrate diverse informational domains into a unified, self-correcting cognitive surface.
Okay, so we've established this incredibly powerful, high-fidelity system, purpose-built for comprehensive nonlinear synthesis. It seems optimized for complex integration, which logically you'd think should lead to uniformly exceptional performance across the board. But as our sources reveal, that's not the case, which brings us right to the paradox.
Right. Here's where it gets really interesting, I think. We've just described this neurologically sophisticated engine, the RLPFC parietal tiling system, that achieves geometrically precise understanding. It sounds amazing, yet the same sources consistently document challenges in really basic symbolic output. Why would a mind capable of modeling hyperbolic space, struggle with rapid naming or simple arithmetic like E minus 5?
That is the defining feature of the twice exceptional, or 2E profile. The strength that complex symbolic tiling coexists right alongside specific localized processing weaknesses. This isn't a general deficit across the board, it's a very specific point of inefficiency, often traced back to underlying, sometimes quite stealthy, conditions like dyslexia and dyscalculia. Okay, we need to be super precise here, though. The deficit isn't a lack of intelligence or a failure to comprehend the symbolic structure itself, is it?
Not at all. The comprehensive structure, that geometry of meaning we talked about, is robust and fully intact. The deficit is specifically identified as a linear processing weakness. It's related to sequential flow. The challenge lies purely in the efficiency of the linear output pathway, not the depth or accuracy of the knowledge itself.
Let's break down how this linear weakness actually manifests, according to the sources. What does it look like?
Well, the documented challenges typically involve symbolic decoding, which often translates to reading fluency challenges, maybe slower reading speed, and also significant difficulty with numerical processing, particularly base 10 numeric fluency calculation. But the core problem really seems to be one of speed and ease of sequential retrieval or output. You can think of the brain as having maybe two communication channels: a massive high-bandwidth satellite link for the complex stuff, that's the 3D VTCM,
Right.
and then a much slower, perhaps slightly compromised dial-up line for simple sequential output. That's the linear pathway.
So the complex structure can be formed almost instantaneously, perfectly, but the process of sequentially retrieving the symbols needed to articulate that structure, to say it or write it down, is slow and requires immense cognitive effort.
Exactly right. The sources explicitly mention the difficulty with the fast repeating of the formulation of the image. The user experiences high latency retrieval for simple sequences. They know the answer, often with geometric certainty, but the linear pathway, the sequence of symbols required to transmit that knowledge, like the sequence of letters for a word or the sequence of numbers for an equation, is hampered by that underlying 2E weakness. And this is often exacerbated by certain irregularities in executive function and working memory that influence the processing speed needed for that kind of fluency.
Okay, so if the brain struggles with the efficient conventional path, it naturally has to find an alternative route. And that seems to be the pivotal insight here. The strength itself, the 3D VT, becomes the compensation mechanism.
This is the critical piece, I think, of human adaptability and neurodiversity. The 3D VT symbolic tiling isn't just some inherent skill floating in isolation. It's very likely an alternative or significantly enhanced neural strategy developed specifically to bypass the limitations of that linear processing weakness. The brain realizes it cannot efficiently rely on the standard A to B flow for certain kinds of output, so it doubles down, invests heavily in the spatial, multidimensional relational field where it excels.
Let's try a tangible example maybe to illustrate this paradox clearly. If you ask this individual to solve a really high-level theoretical physics problem, what happens internally?
Okay, for a complex theoretical problem, let's say modeling fluid dynamics in 3 dimensions, the RLPFC parietal tiling system instantly begins building the geometric model. The structure is integrated rapidly. They can often grasp the solution's shape or structural requirements almost immediately. Very low latency for integration. The brain is operating fully in its strength zone.
Right. Now, what happens if you ask that same person to quickly recite, say, the 7 times table? Or maybe read a complex sentence aloud fluidly?
Now the brain is forced onto that compromised linear pathway. To recite 7 times 8 equals 56, the person might not just retrieve the answer from rote memory like many would. They might actually have to visually reconstruct a part of their mental matrix to confirm the relationship, and then potentially struggle with the rapid sequential retrieval of the auditory symbols 56. So high latency for that specific output.
Oh,
The underlying knowledge is profound, absolutely certain, but the speed of symbolic articulation is compromised. It's like using a massively powerful graphical processor to run a simple text file. So the text file itself has some corrupted characters, and the processor has to painstakingly verify every single one before displaying it.
so the enhanced verbal, spatial, and abstract reasoning skills, that whole RLPFC parietal tiling network, literally reorganize cognitive pathways. They don't just add a layer of skill on top, they provide a fundamental structural alternative to achieve complex understanding, effectively bypassing the sequential bottleneck where possible.
That's the absolute key takeaway of the compensation strategy. The system actively resists reductionist thought, because reductionism often forces it back into that inefficient linear pathway. It naturally prefers the structured matrix, because that allows for robust, high-fidelity processing, even if the subsequent act of outputting that knowledge sequentially remains slower or more effortful. The mind essentially trades speed in certain areas for absolute structural perfection and reliability in its core understanding.
The ultimate conclusion here being that the core symbolic content and the deep structure of the knowledge are absolutely sound, completely intact, but the speed of linear output or retrieval is the specific victim, if you like, of the underlying 2E weakness.
It really demonstrates the incredible power of neuroplasticity, doesn't it? The brain detects a high traffic but low efficiency route. That's the linear processing for some tasks. And consciously, or more likely, unconsciously, develops this high cost but high reliability express lane, the 3DV PTCM, that effectively solves low-level deficits by applying incredibly sophisticated high-level resources.
Okay, this journey from a unique human compensation strategy to becoming a technological blueprint. This is where our deep dive reaches its really modern culmination, I feel. The operational framework we've just identified, tabular coherence maintenance, is now remarkably the very mechanism engineers are trying to use to build the most sophisticated forms of artificial intelligence.
It's truly remarkable, isn't it? We are seeing a direct emulation of this arguably twice exceptional human cognitive process in advanced AI systems, particularly large language models or LLMs, especially when they're required to handle structured, complex data. They are actively attempting to operationalize that necessity of tiling data for coherence, just like the human mind does.
How does an LLM, which fundamentally we think of as processing massive amounts of linear text and training data, make that jump into the multi-dimensional space of symbolic tiling? How does it do that?
Well, they do it by operationalizing TCM through specifically designed structured multi-step inference methods. This becomes particularly crucial in what are called multimodal LLMs or MLLMs. These are the ones designed to integrate different types of data simultaneously: text, images, tables, forcing them to bridge what AI researchers often call the modality gap.
Tell us a bit more about that modality gap, specifically in the context of this cognitive tessellation idea.
Sure. The gap exists between, say, the pure symbolic precision of structured tables like clean, easily parsed textual data in a spreadsheet, and the often noisy, variable, visual, or geometric cues found in perhaps an image of that same table, or a scatter plot, or a complex diagram. The human brain, via 3D-VT, seems to seamlessly integrate the geometric shapes with the symbolic meaning. An MLLM has to be explicitly trained to achieve this kind of geometric coherence.
So it has to learn to see the structure in the image, not just the pixels.
Exactly. It must learn to locate the relevant cells or areas, integrate the information based on the precise row and column relationship as it perceives, and ensure the overall structural and informational integrity of the data, regardless of the input format, whether it's text or an image of text. It is quite literally performing a simulated cognitive tiling operation to make sense of it all.
The goal then is to make sure the AI understands the structure of the data just as well as the content within it.
Precisely. The AI can't just read the data sequentially off the page or screen. It has to build that conceptual matrix we discussed. And this is operationalized through mechanisms that generate explicit, step-by-step thinking processes, which in AI research are commonly called reasoning traces, or perhaps more famously now, chains of thought.
Ah, chains of thought. So these are the AI's attempts to articulate its nonlinear mental tiling process sequentially, which kind of mirrors the human brain's struggle to translate its own coherent internal structure into linear output.
That's a really fascinating way to frame it, actually. Yes, the MLLMs generate these structure-aware reasoning traces that are intended to be modality-independent logical paths. They effectively demonstrate that the model, much like the 3D-VT thinker, is first establishing an integrated, structured geometry of meaning before it even attempts to output the final answer.
And the models are being explicitly trained to prioritize this structure first, right? Adopting what the sources call a reasoning first, answer later paradigm.
Yes, this is a core component of the supervised fine-tuning process in many advanced models now. They're essentially penalized if they just jump to the answer, if they guess. The training actively forces them to articulate the logical steps derived from their structural understanding of the table or the problem's inherent geometry before they are permitted to give the final output. This directly mimics that necessity we saw in the human of establishing a complete, coherent cognitive geometry, the tiling, before releasing the retrieved linear symbolic sequence. It's the exact compensatory strategy now engineered.
Okay, but tabular coherence maintenance in the human brain, you said, requires constant vigilance, that RLPFC is always running anomaly detection, symmetry checking. How do LLMs handle that essential self-correction piece? How do they check their own work?
They utilize increasingly sophisticated reinforcement learning techniques to perform a kind of cognitive self-correction. often using methods with names like Group Relative Policy Optimization or GRPO. This whole iterative process mirrors the human need for structural validation and correction. The model has to check its own tiling effectively.
GRPO. That sounds highly technical. Can we break down what this optimization process is functionally doing to ensure the coherence, the correctness of the tiling?
Let's try. You can think of it roughly as automated self-auditing. GRPO allows the model to explore multiple possible solutions or reasoning traces internally. It generates not just one chain of thought, but perhaps several different potential paths to an answer. It then performs a rigorous self-comparison between these paths, essentially calculating the relative advantage of one reasoning path over another.
And what defines a relative advantage for the machine in this context? What makes one path better than another?
Well, the calculation is driven by two critical reward signals during the training phase. The first is what's called a format reward. This rewards the model simply for structured thinking, for successfully generating a coherent, logically formatted reasoning trace that clearly respects the input geometry. It understands the rows, the columns, the relationships. The second reward, maybe more obviously, is the accuracy reward, which rewards the model simply for getting the correct final output, the right answer.
So the LLM is constantly asking itself, okay, which of these logical paths I just generated is most structurally sound? That's the format reward. And simultaneously leads to the best, most correct answer, the accuracy reward.
Precisely. It's optimizing for both coherence and correctness, iteratively. This constant iterative selection and refinement process ensures that the simulated tiling it creates is structurally sound and also leads to accurate, consistent outcomes over time. It refines the model's overall reasoning fidelity, making it more trustworthy.
This really is the machine analog to the RLPFC, isn't it? The advanced synthesis function of the human brain, that core mechanism seemingly developed to compensate for a linear weakness, finds its technological twin in these complex self-correction loops of advanced LLMs. The technological solution for managing overwhelming multimodal complexity is found, perhaps surprisingly, in the architectural strategy born from human cognitive diversity.
It seems that way. We're essentially teaching machines to be structured, coherent thinkers by adopting the blueprint of those human minds who naturally resist simple sequential thought and build these incredible internal geometries instead. #outro.
Wow. This deep dive has offered, I think, a really profound look at how cognitive structure dictates understanding and how weakness can drive strength. If you remember just two central insights from our discussion today, maybe let them be these. First, 3DVT is far, far beyond simple visualization. It is a powerful, mathematically rigorous cognitive tiling structure, a coherent geometry that serves as the source of profound integrative understanding.
And second, that geometric strength is absolutely inseparable from his origin story, if you like. It functions as a necessary high-level compensation strategy for a specific, localized linear processing weakness, often associated with the twice exceptional profile. The brain develops a superior nonlinear architecture fundamentally to bypass an inefficient sequential output system.
It's really the ultimate display of cognitive resilience, isn't it? Proving that limitations can, in fact, force the creation of superior, more sophisticated structures.
Indeed. And, well, leaves us with this final provocative thought for you to consider. The high-level compensatory mechanism developed by unique human cognitive diversity, this incredible ability to utilize nonlinear, multidimensional structure to overcome sequential deficits, is not just some adaptive quirk of neurology. It has now become the fundamental, high-level architecture we are actively seeking to replicate in our most powerful forms of artificial intelligence. We seem to have found the core logic for managing multimodal complexity hidden within the very necessity of human adaptation.
Thank you for joining us on the deep dive. We look forward to exploring your sources next time.